We ended the first part of this video series by talking about the weights and the need to understand how the weights are derived. We said that the analog signal could be represented by an equivalent set of sinusoids which were weighted appropriately. Now, if that is true, which it is, by the way, that means that we should be able to take the analog signal and then plot each of our harmonics and compare those harmonics with the signal, and we should be able to write down a number which is a measure of how well the signal and the harmonic match. So in our case here, we might be able to say that, oh, if we look at the analog signal, we compare it with this black trace here, then there is some resemblance, if not in phase, then at least in frequency. So there's a good match there. Then we would of course look at the next harmonic. We might find it difficult to see that harmonic, but the principle is that we should be able to compare each harmonic with the signal and give it a measure of how well they match. Now, what I've just said, it has a name, and that name is of course correlation. When we compare signals like this, so we're going to now consider correlation. Of course, we are going to use a computer to calculate the Fourier series, and therefore we need to understand what correlation means mathematically. So we've described what we're doing when we're correlating things. We do it every day in our lives. We look at people, we look at objects, and we compare them with either something stored in our memory or with others, and that is basically correlation. But let's write down what correlation is mathematically next. So let's go to the next page. Okay, so I'm going to write down the word correlation again. Correlation. And mathematically what we're doing is we're taking two signals. So in our case we had our analog signal. We want to compare it against a set of sinusoids. So this time we're going to use e to the power of minus j 2 pi L rather than k f naught t. So we multiply these two signals together, and then once we've multiplied the two, we take the products and we sum them together. Now we're dealing with continuous signals here, so summing is integration, and we're going to integrate over the fundamental period. And by the way, the fundamental period is 1 over f naught, which is the lowest frequency. This is correlation, or it is a form of correlation. So, and of course the result is a measure of how well two things match, so let's give it a name. So we're saying x car is a function of L, and when we plug L in here, we are generating a particular harmonic, and the frequency of that harmonic is equal to L times f naught, and we are comparing our signal against this harmonic and then summing the result up to give us our final correlated measure. So let's put the two equations that we've described now together. Earlier on we had something which said that the analog signal could be recreated by taking a set of weights, multiplying them with or weighting a set of sinusoids with the weights, and therefore and thereby recreating the signal. So what we're going to do is combine these two equations now, and that will relate CK. So we want to relate CK to XD in a way where we can calculate the values for CK. Because the first time I came across these sets of equations, I did wonder, how do you calculate the values, for the weights? So let's substitute this expression here, or I should really say that let's substitute this expression into here. So we're going to write down x correlate, which is a function of L, is equal to the integral over the period Tp. And now we carry out the substitution. So let's use a different pen for this purpose. So let's just get rid of that. Choose a different pen and sum from k minus infinity to plus infinity. So we have a lot of weights. Ck. Then we had e to the power of j2 pi. So these are the set of sinusoids that we are weighting, we are modulating, and then of course that's the end of the substitution. So let's change the pen back to black. We're going to multiply by e to the power of minus j2 pi L f naught t dt. So here's my first reason and my first justification for exponentials. We of course have two exponentials here, and they are using and they both have exponents, and as we know, if you multiply two things with exponents, then the exponents will simply add. So we can simplify. We can also see that ck is the only variable here that's a function of k. So we can move that out. We can interchange the summation. So the summation is going to go outside. We can do that because it's not going to make any difference to the final result. So we have ck on the outside. Everything else is dependent on time. So that's going to be inside the integral. And now we're going to simplify our lives by combining the two exponentials very easily. J2 pi is common, so that's going to go outside. F naught is common. And then in brackets I will write down k minus L, because those are the two terms which differ in the two equations. And of course t is on the outside because it's common. So you can see that we have a simplified expression now, but of course that's not the end. On the next page we will simplify this further. So let me just go back. Let me just see if I can actually copy this expression and take it to the next page. Yes, I can. Saves me having to write it out again. Slightly off the page. That's better. Okay, sorry about that. Right, so we have the expression there, and we're going to simplify by considering two cases. So let's just consider the case. So case number one, which is when k is equal to L. So actually, so what happens when k is equal to L? Well, if k is equal to L, then k minus 1 will become 0, and if that becomes 0, then it makes life a lot simpler, because if we think about anything to the power of 0, so for instance 1 to the power of 0 is the same as 10 to the power of 0, which is the same as x to the power of 0, which is the same as e to the j0, and of course the answer is always 1. So we're going to write down x car L, function of L, is equal to the summation from minus infinity to plus infinity, and then we have our integration, and of course e to the power of j0 is going to be 1, so we're just going to integrate the constant 1. But that's not all actually, because we are considering one case here, which is where k is equal to L. So we can say that this doesn't make any sense. We are not summing from minus infinity to plus infinity, and of course k and L are the same thing now, so we could write CL. So now if we integrate and take the limits, we have CL. We are integrating 1, which is going to give us t. These are our limits, and of course the answer is simply CL TP. So that's one case. If we now write down what x car was earlier on, x car was a measure of the correlation, and we said that to correlate something, to correlate two signals, we would take those two signals, in our case our analog signal, and the set of harmonically related sinusoids, multiply them, and then integrate them, integrate the products. So now we're saying that this expression is the same as CL dot TP, which means that CL, which is the same as CK, is equal to 1 over TP. We integrate over the fundamental period, and what we integrate is our signal with the set of harmonically related sinusoids. Of course, we have one more case to consider. So now on the next page, we're going to consider case number 2, and that's when k is not equal to L.